Welcome back to Chapter 3. In this chapter, we're going to be looking at quantitative data. Last chapter, we looked at categorical data, and we had things like bar graphs and pie graphs. And this chapter, quantitative, we'll get the histograms, the dot plots, things like that. There are some things that are very, very similar, but these two types of data are very, very different from each other. And the things that look similar are actually very much not similar. So let's take a look at our learning targets for this chapter. We'll be able to analyze the usefulness and appropriateness of given display of data, determine how extreme values affect measures of center and spread, create a display of data and describe the distribution and unusual features, and then describe features of a distribution and appropriate measures of center and spread, and then finally calculate the measures of center and spread. So the first thing we're going to look at is histograms. A histogram looks a lot like a bar graph, but it's most definitely not. A histogram is what we use, one of the most popular ways of graphing quantitative data. Now, differences between histograms and bar graphs. In a bar graph, the bar is centered on the category because it's telling us how many of that category happened. With a histogram, they're not centered on a category. In fact, they go in between numbers. So like here, from 80 to 90, we have a bar. That would be the number of cereals that had calories within 80 and 90 calories per serving. We had, it looks like 1. Then the next one, it would be how many types of cereals had calories in between 90 and 100 calories per serving. Looks like that's about 7 of them. Now, we don't know what those are. It could be 91, it could be 93, it could be 94.72. Like it's a continuous variable. It's not a discrete variable, and so it could be anything in the middle. Histograms, unlike bar graphs, do not have gaps in between the bars. If there is a gap in between the bars, like there, that means that there was nothing there that happened. There were no cereals that had between 60 and 70 calories per serving. It was either less or more. The y-axis, again, just has a frequency. That's the count of how many of them happened. And that's what we look at for histograms. Stem and leaf display, also called stem plots. This is another way of graphing category or quantitative variables, quantitative data. It actually looks like a histogram. The nice thing about it is with the stem and leaf display, we can actually get the data back. With a histogram, we can't get the data back out of the histogram. We don't know where that was. But a stem and leaf graph keeps the data, or perhaps rounded data. So for this, we're going to get a data set. We're going to use this data set. I don't have any units or anything for this because, like all good data, I made it up. We could actually go straight from here. This is called raw data. It's not organized or anything like that. It's just the order that it came in. We could go from here. A stem and leaf plot or stem and leaf display does not have to be in order, but we're going to put the data in order just because it makes it a little bit easier if it is. So to make a stem and leaf display, the stem comes from the first digit. In this case, the first digit is the tens column. It could be the first digit's a ones column. If all of these were, instead of 12, it was 1.2, then the first digit would still be a 1. Like, it does not matter what other numbers, like where there's the decimal point in these numbers, the stem and leaf plot actually looks the same. There's a key that we'll put at the bottom of the stem and leaf plot that tells us what those numbers are, but the stem and leaf plot looks the same. If we had numbers in the hundreds, like let's say instead of 12 it was 124, we'd still just use 120 because those first two digits are going to be what really matters. And so we only look at the first two digits of any of these for stem and leaf plot. So to make them, we're going to put those tens digits in the stem. Being that we only have 3 digits, we have numbers in the 10s, the 20s, and the 30s, I'm going to split them. You can split them two different ways. I mean, you can have the unsplit, where like all the 10s are in one, all the 20s are in one, all the 30s are in one. Or we can split them where the first five, 0 to 4, so like 20 to 24 will be in one stem, and then 25 to 29 will be in the second stem. Notice each of those has 5 numbers in it. Or you could split them where there's only 2 in a given stem. It's like 20, 21, and then 22 and 23, and 24 and 25. If our numbers are like all in the 20s, that's probably what we'd want to do for that, because that's where it is. It's kind of like zooming out. That value, just like the width of a histogram, is called the bin, or sometimes the bin size, or also sometimes the bucket or bucket width. That's how much do we want in each bar. Having it too big makes it so we have very few bars, and it's really hard to see anything, and you don't spread anything out. If we expand it so each of them is too small, we get like one data point in each of them, and it again doesn't really tell us anything. So having a good bin size is important in making a graph. So we're going to use, we're going to split it once. So we'll have 2 in the 10s, so we have 2 1s, we'll have 2 2s, we'll have 2 3s. We make our line. And now we're going to make the leaves. Those are the stems. The leaves, so the first one we had is 12. So we put the 2. Now if we look at the stem and then the leaf, we get 12. We get our data back. The next ones are 16. Those are in the upper half of the teens, because it's 5 or bigger. So we'll go 6, then there's another one, and then 8, and then a 9. And then we have a 20, a 21, a 21, 23, a 25, a 25, a 26, a 28, a 29, a 31, and a 35. So this is our stem and leaf plot. If you tip your head to the right, you can see it looks kind of like a histogram. One thing to notice about the stem and leaf plot is I made each of my numbers about the same size. So we have the first numbers right there, then we have the second, then the third, then the fourth, then the fifth. That way, if I have 5 numbers, it's the same size as the other place when I have 5 numbers. If I have 4 numbers, it's just a little bit smaller. I didn't squish the ones together like you can, because ones aren't very wide. You don't want to do that. Think about making these kind of like you're making it on graph paper, where each number gets its own little box. So that's what stem and leaf displays look like. If we wanted to see the histogram in it, well, let's use a different color. We could make the box is just a sideways histogram, which actually you can do too. Histograms can be sideways. And so there's a histogram. You turn your head to the right, it goes from biggest to smallest, but still a histogram. A dot plot. A dot plot's kind of similar. A dot plot, we actually start out with a number line. So we have the 10s, it's 15, 20, 25, 30, 35, 40. And then for each point, you make a dot. So we had 12, so we put a dot at 12, and then we had 16, so we put a dot at 16, there's another dot, and etc. And you just put a whole bunch of dots. My pen and the computer doesn't like to make dots, so a lot of times it will think it's doing something else and pull up a menu, and sometimes it completely bombs me out of the program. So I'm not going to make too many more dots. But those are stem and leaf displays and dot plots. And again, dot plots are another good way of just kind of taking your raw data and organizing it into a quick little graph. Shapes of a distribution. There's always something we do when we're describing a distribution. When we're describing a distribution, what we always have to do is we have to cuss. That means, no, not what you think it means. Yeah, I know, you've been doing that for years in your math class. No. When we're describing distribution, we need to talk about the center. We need to talk about unusual points. when you talk about the shape, and when you talk about the spread. So when describing a distribution, you could actually make 4 sentences if you wanted to. 1 sentence for each of them. That works. You don't have to do it that way. You could do more, you could do less. But you want to make sure you hit each of those things. Sometimes, like if there are no unusual points, like on the AP test, if you don't say that, oh, there are no unusual points, it doesn't matter. But sometimes if there is, like they look for each of these things, like it's actually like a little checklist. So if you always do that, then it gets you those points pretty easily. So the shape of a distribution. First thing we want to look at, how many modes are there? And you might be thinking like, wait a second, a mode, that's one of the center, mean, median, mode. It's a measure of center. Yeah, kind of, but it also is the shape. A lot of graphs, like the histogram that we saw earlier, is called unimodal. It has 1 mode, and that means that it had 1 point. And you might be thinking like, wait, well the stem and leaf plot, there were 2 things that had 5. That's okay. It was still right there in the center. So for the mode, we're not necessarily looking for the one value that happens the most. We're looking for the peak of the graph. Because if our data was spread out, let's say if I took the height of everybody in the class, and there's 30 some odd people in the class, it's very possible that no height will happen more than once. But we're going to have a lot of people in that like 5'8" to 5'10" range. That 5'8" to 5'10" range would be where the mode is. Because even if like you might be 5'8" and the next person's 5'8.1, like you're not technically the same height, but you're really close. And so for the mode, we're looking at the peak. A unimodal graph has 1 peak. That's what we're going to be dealing with for most of the year, because we'll be looking at the normal curve, and the normal curve looks like that. We can have a bimodal graph. Bimodal graphs have 2 peaks to them. A lot of times test scores will be bimodal. We'll have a group of people that knew what they were doing, that did pretty well. There's some variability there. And a group of people that didn't know what they were doing, that did not so well, with, again, some variability. But there's those 2 peaks with very little in between, remarkably enough. And so, and if it has more than 2 modes, it's just called multimodal. They don't go to like trimodal and quadmodal, it's just multimodal. Then there's also what's called a uniform graph, which has no mode. Now, some people think uniform graphs are just like rectangles, like it's just everything's exactly the same. That's not entirely accurate. It doesn't have to be exactly the same. Like in this little sketch of a histogram I made, they're not exactly the same, but they're pretty close. Nothing stands out as this happened more than anything else. That's what we'd be looking for the mode and for the shape. So the shape of distribution, how many modes? Unimodal, bimodal, uniform. If it's bimodal, sometimes it's a good idea to pull the variables apart too, see what happened. For instance, if we were looking at the height, I don't know about this class particularly, but if we're looking at the height, we might get a bimodal graph because the guys can tend to be a little bit taller than the girls. And so if there's a bit of a split there, we might have like a mode, like a part of the graph for the girl's height and a part of the graph for the guy's height. And so splitting the 2 apart might give us a better description of the data. And then the next thing is symmetric or skewed. Symmetric just means that you can kind of fold it in half and it'll be about the same. It will most likely not be perfectly the same. That's fine. Statistics, it doesn't have to be perfect, but it's about the same. It looks about the same on both sides. So that graph right there is symmetric. In fact, all 3 of those that I drew are basically symmetric, because if you fold them in half, it's about the same. Skewed, we have 2 different types of skewed. We have the type looks kind of like that, and we have the type. Looks kind of like that. The skewed, one of them is left, one of them is right. This one is left skewed. This one is right skewed. The way to tell, the tail points the direction. The tail is the little part that's like really going out, where you might have your outliers, which we'll be talking about in a second. That points the direction. When the tail's pointing to the left, that points that direction. When the tail's pointing to the right, it means it's a right skewed. Different things have different skewedness. Generally speaking, if there is a bound, that will make it so that it's skewed away from that. For instance, the left skewed graph is a lot of times what test grades will look like as well. If it's not bimodal, it'll be left skewed because there's an upper bound to the points you can get. Yes, I know there's also a lower bound of 0, but most people aren't even close to that. They're kind of gathered up in the upper bound. It's just like, did you get them all? A few people get every point, and then some people miss a few. Like some people miss a little bit more, and then you get fewer and fewer people getting lower and lower scores. And so when you have an upper bound, you tend to get a left skewed graph. When you have a lower bound, you tend to get a right skewed graph. For example, the incomes in any given region or the US or something like that. There is a lower bound for an annual income. That lower bound would be 0. And then you have, a few people that are making right about that. And then as you increase the income, the height of the graph goes up. And so you have a lot of people making the median or the average type income. And then as the income increases, you get fewer and fewer and fewer people making it. But there is no extra. We have like Jeff Bezos over here, and we have Bill Gates over here, and we have Elon Musk over here. And so you have like those guys which are pulling the tail that way, but you can't have anyone over here less than that 0. So when there's a lower bound, it tends to make it right skewed. And then outliers. We'll be looking at different ways of judging outliers, like is it an outlier or not? But an outlier is something that doesn't fall with the rest of the data. It's really big, it's really little, it's just outside of what you would expect. When you have an outlier, you always want to address it. You need to discuss it, and by discuss, I don't mean that it's a two-way conversation necessarily. You might be writing like a report or so. Discuss means you need to talk about it, you need to write about it, you need to notice that it's there and give an explanation possibly for what it could be. Now, an outlier could be an outlier because a mistake was made. Maybe the data was entered incorrectly and that could actually be fixed. Maybe an outlier is just you randomly happen to have an outlier. Like if we got like a random assortment of people and we were looking at their income, it's like, hey, most people are making kind of like a normal average thing, but in our random assortment of people, we also happen to get Bill Gates. Oops. Well, that's fine. He's part of our data, but he's going to definitely be an outlier. And so we need to discuss that. Then do you keep it? Do you not keep it? What do you do with it? That depends on what you're doing. That depends on the outlier. That depends on a lot of stuff. One of the videos I assigned with this does a fantastic job of explaining it. So I'll leave that to him. So one of the measures of center we have, so that was all about shape. Now we're looking at center. One of the centers is the median. So the median, let's get our data. The median is the middle number. It also splits a histogram into equal areas. So to find the median, we first need to order the data from smallest to biggest. And then we can either count and find the middle number, or we can start crossing things off. We have the smallest and biggest get crossed off, the next ones get crossed off, the next ones. So I'm just crossing off a small one and a big one until I get to the center. This works since it's a pretty small data set. If you had a really big data set, that would be kind of obnoxious. And we get to the median is 21, which being that it happened to also be in 2 rows, that 21 shouldn't have been too surprising. And so that's the median, it's just the middle number. If we looked at the histogram for this, that would give us equal area under the histogram below 21 and equal area above 21. The spread. So this is a spread that we would look at while looking at the median. So this whole slide has to do with when we're measuring things using the median. So ways of looking at the spread, there could be the range. The range is just the smallest or the biggest number minus the smallest number. So for us, the range would be 35 minus 12, which is 23. So the range is 23. It's not 12 to 35. It's 23. It's what is the distance between the smallest number and the biggest number. It does not tell us where it is, just what that distance is. The interquartile range is another one. Like the 23 is pretty big. That tells us how far spread out the data are, but it doesn't give us much more information. For the interquartile range, we first need to find the quartiles. To find the quartiles, we're going to look back up at the data where we found the median. So when we find the median, that splits the data into 2 equal sets. We have the lower set, we have the upper set. The quartiles are going to be just the medians of those. So if we look at the lower set, actually we can do both at the same time because we can cross off the lowest and the biggest, the lowest and the biggest, the lowest and the biggest. Just how it happened to be ordered, we were able to do that. And now we're left with the middle ones. And we have 2. With the median, we only had 1. Great, it's the middle number. Well, what if we had an even number of things? We have 2 things in the middle. We just find the average, add them together, divide by 2. So this top one is going to be 16 plus 8 divided by 2, which is 17. And the bottom one is 26 plus 28 divided by 2, which is 27. On these, you can probably also look like, what's going to be right in between 16 and 18? 17. So the first quartile, Q1, is going to be 17. And the third quartile, Q3, is going to be 27. You might be thinking to yourself, wait a second, what happened to the second quartile? The second quartile is the median. We just call it the median, not the second quartile. So the interquartile range, which is also abbreviated IQR, by the way, is just going to be 27 minus 17. So the interquartile range is 10. So we can find the range, we can find the interquartile range. And what that is it's the middle 50% of the data. The middle half of the data is within 10 units of each other. That's what the interquartile range tells us. We have a 5-number summary that we're going to use. And a 5-number summary, we've actually already found all the pieces we need for this. A 5-number summary is going to include the minimum number. It's going to include quartile 1. It's going to include the median. It's going to include quartile 3. And it's going to include the maximum number. So the minimum was just 12. The maximum was 35. It's the smallest and the biggest. The median we found was 21. And the quartiles were 17 and 27. That's what the 5-number summary does. It gives us a bit of information about the data in a fairly short amount of time. And it also allows us to create a box plot, also known as a box and whisker plot. Now these can be created both horizontally and vertically. The book does it a lot more vertically than horizontally. I have always preferred it horizontal, so I'm going to make mine horizontal. You're probably going to see some vertical ones when you're reading. But with a box and whisker plot, or a box plot, we're going to start with a number line. And this number line is going to be numbered with equal spacing. That's one of the things I see a lot, is people will number it with with the numbers that they need and not as an actual number. And so their box plots are always like symmetric, even though they really should not be. Label the number line first, then draw the box and whisker plot. For that, the whiskers, the very ends are going to be your minimum, maximum, and they're just going to be little vertical segments. Minimum, maximum, and they're right on level with each other. And then the quartiles and the median are going to have bigger vertical segments. So we have 17, just right about here, 21, 27. And now we connect the tops of those bigger ones. That's your box. And then from the center out to the whiskers, that's your whiskers. So you have your box and whisker plot. 50% of the data is inside the box, and then you have 25% on each end. In fact, there's 25% in each of the sections of the box. That's why it's called quartile. It's 25% in each of those places. So that's what a box plot looks like. A box plot and a histogram are graphed using the same data, but they can give you very different information. A lot of times I like to graph both because they get deciphered differently. The other measure of center is the mean. The mean is just the average. It's also the balance point of a histogram. Remember that the median is the equal area point. The mean is the balance point. So if I were to put a histogram up on a pin, you put it on the mean and it'll balance, even though it's not equal area. Because the further away something gets, the more it'll kind of tip it that way. To find the mean, it's just you add up all the values, you divide by the number of values. N is pretty much always in statistics the number of something. It's the sample size. It's the number of things that you have. That's what N always is. This notation right here is the mean. It's pronounced X bar because there's a bar over it. It's X bar. In statistics, we get all sorts of fun variables and accents and stuff like that. Later on, we'll get something that looks like this. It's called p hat. That's how it's pronounced. It's just p hat. We're not going to do that now, so I'm going to erase it. That's just a little teaser for later. So, X bar, and if we had, if our variable was y, it would be y bar. So it's just, the bar just means average. And I know the equation looks kind of weird. It's the same average that you've always used. It's just you add them all up, you divide by the total number. That's just how you would put it into an equation. So now the question is, do we use the mean or the median? Well, the mean we generally use if it's symmetric. And the median we would generally use if it's skewed. Because the median is what's called resistant. Because what happens is if you have an outlier, it doesn't really change the median much. It might move it a little tiny bit, but not much. Because it's resistant to outliers. A mean, however, if you have an outlier, it's going to move the median. It's going to move the mean a ton. One of the things I generally do in class is I get age data from everybody. And you guys are all probably between 16 and 18, maybe a couple 15s in there, depending on who's in the class. But your average is probably going to come out to be about 17 point something. Depending on the size of the class and what you guess my age is, if I add my age into it, the average age for the class comes out to be like 20 or 21-ish. And so that's not a great descriptor for the average age of the class. But that is what an outlier will do to the mean. This is another topic that is explained amazingly well in one of those other videos. So make sure that you're watching those. They are really, really good. And getting these two mixed up in which one would be better to use is a common mistake. Throughout the rest of the year, we generally use the mean because what we're dealing with is going to be symmetric. and because the mean is something we can actually use in an equation, because it uses an equation to find it. The median is a good descriptor, but not so good to use in equations. And then the spread. With the median, our spread was the range or the interquartile range. With a mean, we use the standard deviation. The standard deviation is basically the average distance away from the mean. But we can't just find the standard deviation. We first have to find the variance. The variance is the average squared distance from the mean, because if you just took the average distance from the mean, you'd come out to 0, because the stuff above counteracts the stuff below. That's what the mean does. So we square all those values, which makes them all positive. Then we find the average. So that's what this says. We have the x minus x bar. That's the distance away from the mean for each of our values. We square those numbers to make them positive. It also makes them bigger. I have seen somewhere that they found instead of the standard deviation, they called it the standard variance, in which case they just took the absolute value of all of the distances and averaged them. But this is the typical way. Standard deviation, the variance, we square all those distances, we add them up, and we divide by the total number almost. Divide by the total number minus 1, so it's 1 less than the total number. And that gives us the variance. The symbol for variance is s squared. Sometimes we use lowercase sigma squared, but that'll be more for the population, not the sample. And so that's the variance. Then the standard deviation, we need to get rid of the squared because we're using a bunch of squared values and it's not in the same scale as what we need. So for the standard deviation, we just square root that. So the symbol for standard deviation is just s, because what's the square root of s squared? It's s. And so it's just a square root of the variance. And that gives us kind of the average distance from the mean of the points. And we'll be using standard deviation a lot as the year goes on. We'll be able to understand it a lot more. Right now, it's just the average distance from the mean. The bigger the standard deviation, the more spread out the points are. If you want a standard deviation of 0, they all have to be exactly the same number. And then what can go wrong? There's a lot of things that can go wrong, and I love that this is part of each of the chapters, because I see these mistakes all the time. First, don't make a histogram of categorical variables. Categorical variables and quantitative variables are different. They need to be treated differently. They look similar sometimes, but it's a lie. It's a trap. Second, don't look for shape, center, and spread in a bar chart. Don't treat a bar chart like a histogram. First of all, the bars, you could rearrange those bars however you want. So shape, center, and spread, like you could make it bimodal if you wanted to, as long as there were peaks. Don't use bars in every display. This is a big one. I've seen people do time graphs, which a time graph should be like points connected by segments. And I've seen people make bars. Don't do that. Like, bars are only for bar graphs and histograms. Other graphs have their own things that you need to use, and they're not bars. It looks ridiculous and it's incorrect. Choose bins appropriate to the data. We've talked about that. If it's too few bins, which means the bin width is too much, like you could have just one bin that has all your data. It's not going to tell you anything. Or if it's too many bins, you have like one thing per bin and a whole bunch of empty bins, and that also doesn't tell you anything. Generally speaking, for a histogram with a normal type range, like 7 or so would be a good number, 7 bars. Sometimes a little bit more, sometimes a little bit less. If you have a ton of data, maybe you have a lot more, but 7 is a good thing to shoot for. Don't forget to do a reality check. Does it make sense? If you have an outlier, does that outlier make sense? Like, where did it come from? If you're graphing something, does what you just graphed make sense? Like, was it what you expected to see? If it wasn't what you were expected to see, that does not necessarily mean it's wrong, but you want to take another look to make sure that something horrible didn't happen in the process. Don't forget to sort the data before finding the median. I see this happen all the time. They just take the data, they find the middle number, and it could be the biggest number. It just happened to be in the middle. Arrange the data from smallest to biggest before finding the median. Don't worry about small differences. It could be rounding errors. It could be in finding 5-number summaries, there's not a firmly agreed upon way of finding the quartiles. Do you include the median in your endpoints of quartiles? Do you not? And so there are little differences here or there, but it's not going to affect the overall picture shape. It's just going to be like these little minor things. They're basically just rounding errors. Don't worry too much about those. Don't compute numerical summaries of categorical variables. Again, categorical and quantitative variables are very different. Treat them as such. Don't report too many decimal places. First of all, it's just irritating. It's like, oh, the mean of these numbers is 17.57394213. Just leave it to a couple decimal places. Use one more decimal place than the data. So like in our data that we had, that I had made up, that went from 12 to 35, if we found the mean of that, it would be like 17.3. It's actually not going to be 17.3. That's way too low. It could be 25.3. But just using that one digit, not everything. Same thing with your standard deviation. Use one or maybe two extra digits for your standard deviation, possibly. Watch out for multiple modes. If there are multiple modes, it's a good possibility, but why were there multiple modes? Could the data easily be broken into two different pieces where you had one mode and another mode? Maybe the data would be better looked at separately as opposed to all together. Maybe it should all be together. It's a judgment call. It's something that you want to look at. So notice this doesn't say no multiple modes. It says just watch out for them. Beware of outliers. Why is it an outlier? Was it a mistake? Was it, is it good data that just doesn't fall into the overall pattern? Either way, you do want to be aware of them because it will affect the mean, it will affect the standard deviation pretty substantially. So again, you want to be aware. And then don't forget to make a picture. Remember the rules for describing data. You need to make a picture, then you need to make a picture, and then you need to make a picture. Because that will help show you what it's doing. It'll help you see patterns, and it'll help you tell other people what the data is about. So be sure to make a picture. Looking at raw data or even tables, it can be very informative numerically, but it's really hard to see big picture stuff that way. So this was chapter 3. This is all about quantitative variables, which we will be using a lot throughout the year. So I hope you enjoyed. I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.